All right, class, so here is another practice problem that has to do with calorimetry and thermochemical equations, and it's a little different than what we've done so far, so I wanted to sort of walk you through it. So in this question, we are told that we've got a pure sample of this sort of crazy 6-methyl-5-heptene 2-one sort of big organic molecule, C8H14O, that's the important bit that we need to use, is combusted in a bomb calorimeter. So remember what a bomb calorimeter is. Here's my picture of that. It's this sort of bomb chamber where we can do a chemical reaction, energy can be released to the water, and then the temperature of the water will go up. So this is what we're going to be sort of utilizing in this problem. If the combustion of 8.88 grams of our C8H14O, so that's going to be the amount that we put into the bomb calorimeter, results in a rise in temperature from 38.46 to 41.60, so the temperature is going to go up. So as the reaction goes, meaning that that reaction must be an exothermic reaction, then the energy is going to be absorbed by this bomb calorimeter. Then the question says, what is the heat capacity in kilojoules per Kelvin of the calorimeter? So right away, based off of what these units are, what we need to be thinking is that we're going to be utilizing some sort of equation that looks like Q equals C delta T. And so this C, that's going to be my heat capacity. So the amount of heat that I put in, right, to heat up this whole thing. It's not just the water, it's the wires and the insulating jacket and all that sort of stuff. That's going to be sort of what is absorbing all that energy. So in that case, it makes a lot more sense for us just to use the C heat capacity term, and the fact that we're given the units kilojoules per Kelvin, that tells us that we want to be using Q equals C delta T. We're not really concerned about the mass of the water because we don't really know that. We're just treating this whole thing, right, the whole bomb calorimeter, as what's going to be heated up, and all of that information is going to be contained in this C term, essentially. The heat of combustion for this organic molecule is minus 4,837.8 kilojoules per mole. So this information here, this is going to tell us how much energy is released from that chemical reaction, and then the calorimeter is going to be absorbing all of that energy. And then we need to sort of put all that information together to solve for this C term. That's the goal of this problem. Okay. So let's go ahead and do the problem. So the starting bits of information here, 8.88 grams. I'm going to need to convert that to moles because I want to use that to figure out how much energy is released. So step one, we might say how much energy is released when C8H14O is burned. Right, so we're combusting it, we're burning in an oxygen, so we want to know how much energy is going to be released in that process. So the first thing I would do is 8.88 grams C8H14O times 1 mole over 126, where to go, 126.22 grams. So if we add up C8H14O, the molecular mass of that is 126.22. This is going to tell us that we have 0.0704 moles of C8H14O. And then since I know the heat of combustion, the units here, kilojoules per mole, this is telling me that this is the amount of energy for every 1 mole, but I've only got 0.0704 moles, so to figure that out, I would just do sort of a conversion factor, moles of C8H14O times minus 4837.80 kilojoules per mole. So my units of moles are going to cancel, and then this calculation will tell me the kilojoules of energy that's going to be released when I burn that organic molecule. So that ends up being, let's see, minus 340.4 kilojoules. So the significance of the minus sign here, that's telling us, one, that it's exothermic, and two, that's evolving that energy. That energy is going to be transferred essentially from this reaction chamber to the calorimeter. So a negative value there means it's evolving that energy. So then two, when you sort of need to look at it from the calorimeter's point of view. So let's write, look at the reaction from calorimeter's view. So what I'm sort of meaning there is that from the point of view of the calorimeter, that's going to be absorbing that energy, right? So that energy is going to be absorbed, and we're going to sort of utilize this Q equals C delta T, where Q, that's going to be this value of energy. Now, since in the reactions case, it's evolving that energy, in the calorimeter's case, it's absorbing that energy. So the sign on Q is going to be switched. So we're going to say this has a negative value because it's giving that energy away. So then the value for Q, from the calorimeter's point of view, will be a positive 340.4 kilojoules because it's absorbing the energy. And that will be equal to C delta T. Now, if we go back to our problem, we know what delta T is, right? 38.46 to 41.60. And remember, delta T equals T final minus T initial. That'll help you keep your signs straight. And in our case, that equals 3.14 degrees Celsius. Now, we got to sort of talk about this Celsius Kelvin conversion here, because we're looking for the heat capacity in kilojoules per Kelvin. Now, if we're talking about a change in temperature, a delta T, it really doesn't matter if we're talking about a Celsius or Kelvin, because the delta T will always be the same, because if you do the change, it's just the difference between the two values. So if I converted these to Kelvin, for instance, and then found the delta T, that delta T would be the same as if I just do it in Celsius, right? We'd be adding 273 to each one, still finding the difference. That difference is still going to be 3.14. So a delta T, doesn't matter if it's Celsius or Kelvin, it's the same thing. Okay, so now we can just solve our final problem here. Plug in 3.14 for delta T and solve for C. Then that gives me a C value of 108 kilojoules per Kelvin. And that is my final answer. All right, hope that helps. And let me know if you have any questions.